The Higgs mechanism is based on spontaneous symmetry breaking of a local gauge invariance. Recall that in the case of a spontaneous symmetry breaking, the Lagrangian keeps the symmetry, is still symmetric under the transformation, but the ground state, the vacuum, is not symmetric. We saw that to get local gauge invariance, we need to replace the covariant derivative by the gauge covariant derivative. So the Lagrangian for a complex scalar field with spontaneous symmetry breaking is given by where the Maxwell Lagrangian has been added in order to take into account the kinetic energy associated with the gauge vector field mu. Let's first look at what happens to the Goldstone mode. Recall that in the case of the global gauge spontaneous symmetry breaking, we had a Goldstone boson which was massless. The Goldstone mode is associated with rolling along the gutter, which means that it explores different vacuum configuration. So as before, we choose one configuration for the vacuum, which for convenience we choose along the real axis, and we expand the Goldstone mode around this vacuum. Let's factorize nu. We recognize the first order Taylor expansion of an exponential. So we see that the Goldstone mode corresponds to a local gauge transformation. But in principle, our Lagrangian is local gauge invariant because we used gauge covariant derivatives, and therefore it should not depend on the Goldstone mode because the latter correspond to a local gauge transformation. Let's verify this explicitly. That's how the gauge field transforms under a local gauge transformation. And the gauge covariant derivative, being itself function of this gauge field, also transforms. The Maxwell Lagrangian is gauge invariant, assuming the gauge field transforms this way. These terms are obviously gauge invariant, and we already shown that the term with the gauge covariant derivative is gauge invariant. So let's do it quickly by applying the gauge covariant derivative to the field and see how it transforms. We want to move the exponential to the left, and we see that only the covariant derivative will act on the exponential because of the space-time dependence of epsilon. The derivatives of epsilon cancel. We get similarly for the complex conjugate term. So the product of d alpha phi star times d alpha phi is obviously local gauge invariant. So when we were using covariant derivatives, we had in the Lagrangian Goldstone mode, which was massless. But now that we are using gauge covariant derivative, this makes the Lagrangian not depend on epsilon at all. Therefore, local gauge invariance makes Goldstone mode disappear. Our second question is what happens to eta, the field which corresponds to climbing up the wall of the potential. And the answer is nothing. We get the same contribution from eta as what we got in the case of spontaneous symmetry breaking of global gauge invariance. The reason why nothing changed for eta is because the gauge field mu is the only thing which appears as a new quantity when we replace the covariant derivative by the gauge covariant derivative, and as you can see, the gauge field doesn't contain eta when it transforms under local gauge invariance. It only includes epsilon. So the eta field is still there. It has a mass, and it is called the Higgs field. So the particles corresponding to excitation of this field on mass shell are called the Higgs boson. Finally, the last question we would like to ask is what happens to the gauge field mu we introduced in order to have local gauge invariance. So the gauge field appears in the Lagrangian because we introduced the gauge covariant derivative. So we need to look at this term in particular. Recall that we expand the field around the vacuum, which we chose to be along the real axis. And we just saw that the Goldstone mode disappears. Therefore, the field remains real as it can only transform along the real axis. This way we see that these two terms cancel. So we see that the gauge field produces an interaction term with a scalar field. So we got three terms quadratic in the gauge field. The first term does not involve the Higgs field. The second term is linear in the Higgs field, and the third term is quadratic in the Higgs field. E and nu are just constant parameters of the Lagrangian. So we see that the first term corresponds to a mass term for the gauge vector field. So we see that local gauge spontaneous symmetry breaking naturally creates a mass term, produces a mass for the gauge vector field, and that's what we call the Higgs mechanism. The other two terms imply interaction between the gauge field and the Higgs field. We see that we have two types of interaction with two different coupling constants. One is linear in the Higgs field and the other one is quadratic, so the corresponding Feynman diagrams look like. In the first one, because there is only one Higgs field, we have only one line corresponding to the Higgs field, which is attached to the vertex, and the Higgs field is represented by a dashed line. In the second one, because we have two Higgs fields, we have two such lines. And because the vertices are different, we should use a different notation to represent the vertex for these two Feynman diagrams. Note also that at least the first interaction term is proportional to the mass of the gauge field, and therefore a massless gauge field, like the photon, will not couple to the Higgs field, at least not through this mechanism.